alter, but it won't be on the next exam.
Okay.
With fall break and all that business. It's just going to be difficult. All right, so remember with this chapter 6, and Drew, I think yours, the quiz on this was due tonight, right? Is that true?
Mm-hmm.
Yeah. So for chapter 6, we have a couple major topics, right? First, this is dealing with momentum, and we can calculate our momentum. P is equal to m times v. Hey Bree, here's the notation. You can just keep that. You'll have that for the exam. So we have a couple big things here. First is that we can calculate the force in a collision. F is equal to delta P over delta T. And then usually we calculate this delta P is going to be m v final minus m v initial. Sort of the stumbling part for people is not getting this v initial right. Sometimes it'll be 0, but sometimes it won't be 0. So we'll look at some questions where we have to play with that. You have to be very careful with your signs anytime you're dealing with momentum, because remember, momentum is a vector quantity, not a scalar quantity. So it sort of changes the way that you work with things. So we'll work through some problems like that in just a minute. And then also, and I don't think in the 3T class that we've really gotten into this very much, but when you have collisions, the conservation of momentum, yeah, we did this in class, right? With law of conservation of momentum. That is that the initial momentum is equal to the final momentum. All right. So if I have a collection of particles, if I add up all of their momenta, that's the product of the mass times the velocity for each one. That should remain constant all the way throughout. All right. So we'll work through some problems like that. And then if y'all have questions, we can also go back to the energy if y'all want and work through some other problems as well. Because as I said, the next test will just be chapters 5 and 6. Chapters 5 and 6. All right. Is that okay? A good plan? All right, let's work through some problems. I'm going to pull up some old test questions. All right, I think I was looking at 09. I got some good ones. All right, we can come back to these energy problems if y'all want some extra practice towards the end. But let's do these momentum problems first. Okay, this is a good one. So I have Alex. This, by the way, is Fall 09, Exam 2. Can y'all see the text okay, Jordan? Yeah. It says Alex throws a 0.15 kilogram rubber ball down onto the floor. The ball's speed just before impact is 6.5 meters per second, and just after is 3.5 meters per second. And it's in contact with the floor for 0.5 seconds. What is the magnitude of the average force applied by the floor on the ball? So we're going to use this idea that our force is related to the change in momentum. F is equal to delta P over delta T. I'm going to give y'all just a minute to go ahead and get started on that. You want to calculate your change in momentum. Be careful of your signs because the signs of the velocities aren't given, but they're implied in the problem. So you need to make sure that you get those correct. I'll give you just a minute to get started and I'll jump in. So go ahead and determine what is your delta P. Yeah, I'll try to zoom in. Let me... Y'all go ahead and start that off. I have to open it, something different. Which problem number was it? Is that bigger? It is bigger. Okay. Is that better?
Yeah.
All right. So we're finding F is delta P over delta T. That's mvf minus mvi over delta T. But since the mass doesn't change, I can just say m times vf minus vi divided by my time. Now most of all these I have. The only tricky part is getting the signs right. What is my final velocity here? That's right. Yeah, 3.5, and that's 3.5 meters per second up. So it's going to be positive 3.5. And what's my initial velocity? That's right, negative 6.5 meters per second. It's negative because it's going down. All right, so you have to do that difference of a negative. Let's see, our mass, I'll go and put in here, is 0.15 kilograms, and then that's divided by the time, which is 0.025. These problems aren't going to change much from this, okay? It's really just a matter of knowing the appropriate quantities. Let's see, this is 10, 1.5, divided by 0.025. Yeah, I did. 60 newtons. So that means that to change the motion of this object, I had to apply a force of 60 newtons. All right, you could also find the acceleration. We worked a problem like this in class, I think, where now that we know the force, that's equal to ma. So A is just F over m, which is 60 newtons, over the mass, which is 0.15, 60 over 0.15, 400 meters per second squared. So big acceleration to make it change direction like that. Also, if y'all remember from the 3D class, you can also just say to find the acceleration, this change in the velocity divided by this time. It'll give you the same answer, 400. All right. Can I take this away? Y'all be good on this? The problems aren't going to change a whole lot. It'll be something like that. You'll be able to determine that it's that type of problem because it'll give the time and it'll give the differences in the velocities. You should also be prepared to, though, like I might give you a force and ask you to define what is the initial or final velocity, being able to solve for any of those variables. Was that a hand up, Bree, or you just, what's up?
Will the initial always be?
If it's going downwards, yeah, but not necessarily. Like I could have something moving in the horizontal plane, or you could always throw something up as well. And, yeah, so it doesn't have to be negative. But you, right, because you're throwing it down is why it's negative.
So why does it turn off and just?
Because it goes to the floor and then it bounces back up, and so it's going down and it comes up again. All right. So a lot of this is just experience. I think that y'all are probably getting better at reading these as you've been going through the class, because a lot of the same things apply now. But just being able to read the problems and determine the signs for various quantities.
Would you ask, like, would there be a question like, what is acceleration, but you would still give the time, the velocities, and you have to find it?
Yeah, I could do that. Mm-hmm. You mean,
like, if that question was just to find the acceleration. Like,
yeah. Yeah, we worked through a problem in class like that. Now, to find the acceleration, you could go through all of this, or you could just say the acceleration is this, the change in velocity over that. And you can find the acceleration like that as well. Let me show you. That's our definition of acceleration. Delta V over delta T. That's going to be this quantity, which is 10 meters per second, divided by the change in time, which is 0.025 seconds. And that is 60, right? Or 400 rather, yeah. Yeah, 400 meters per second squared. All right. But certainly expect to see some problems like the next one, so let's just take a moment to linger on it. In fact, to prepare for the test, you should take those concept tests and just go through and make sure you understand all the various concepts that are related to momentum. But I really like these questions where, can I take this away? Free? Yeah, let me show you. If you go to the concept test, download them as a PowerPoint. If you go to File, Print, you want to print the, print notes. I like to do 6 slides horizontal like that, and then that puts the question on one side, answer on the other. And then this is the thing you want to do. You want to do pure black and white. Well,
It looked like
It shouldn't matter. I mean, we can look at the other. I can help you with it later. Okay. You can try grayscale. I'm pretty sure it's pure black and white though, but you could try grayscale as well. Let's see, where was I? Alright, let's try this. So, if the momentum of an object is tripled, its kinetic energy will be changed by what factor? This is a nice problem actually. So, I have my momentum is equal to mass times velocity. And I'm asking, how is the kinetic energy changed? I know that kinetic energy is 1/2 mv squared. Well, if my momentum is tripled, what does that tell me has happened to the mass or the velocity?
The mass goes up.
Well, the mass actually stays constant, but if this is tripled, what has happened to the velocity? It's tripled, right? So if I get 3 times the momentum, that means I have 3 times the velocity, which means I'm going to have how much more kinetic energy? By a factor of 9, right? Because I have this squared term right here. So if I triple this speed, that means I get a factor of 9 there. So if I have 3 times the momentum, that means I have 3 times the speed. And if I have 3 times the speed over here, that means I have 9 times the kinetic energy. So just knowing those formulae, and then knowing how if one variable changes, how the others change as well. Those are good questions to ask. Take this way. All right, let's try this one. This is a conservation of momentum problem. Remember, with conservation of momentum, it's Pi is equal to Pf. And guys, listen, if I'm going too fast, then please just stop me and ask questions, okay? There's only a few of us here, but if you're not getting something, I certainly want to stop. So when you're dealing with these conservation of momentum problems, you'll know that they're conservation of momentum because there'll be 2 or more bodies that are involved. Actually, practically, you'll only be dealing with 2 bodies, but you could apply it to any number of bodies. And so in this case, our 2 bodies include Anne the astronaut, and then what's the other body? The satellite, right. So what's happening here is she pushes this big satellite away from her at a certain velocity, and then we want to know what is her speed going backwards. So here's Anne. This is the satellite. It looks like an alien robot. And she pushes it. Initially, they're both just sitting there. So initially, my momentum is equal to the momentum of Anne plus the momentum of the satellite. But since both of them are not moving, it's just going to equal 0 kilogram meters per second. So my initial momentum is 0, and then it tells us that she pushes this 350 kilogram satellite at 0.9 meters per second. And so in order for the momentum of these 2 bodies to add up to equal 0, which is what the law of conservation of momentum says, it says that the initial momentum, which initially is 0, has to equal the final momentum, then the momentum of this object has to be equal but opposite the momentum of this object. So there has to be another vector that's pointed in that direction that will give us 0 momentum. So there has to be another velocity here that will cause her momentum to be equal but opposite that of the satellite. So P final will be the mass of Anne, which is 60 kilograms, times her final velocity, plus 350 kilograms times 0.9 meters per second. And that's going to equal 0. And then we solve for VF. Let's see, 350 times 0.9. It's 315. So it's going to be negative 315 divided by 60. It's 5 1/4. 5.3. So that's how you would solve for VF. Okay. There's several problems in the homework that are like this, but they're gonna, really those are the two types of problems that you have to work. One where you determine the force involved, or maybe some other quantity that's there, like an initial or a final velocity, where you have one object that's colliding into some, or is changing velocity in some way. Like we did the football problem, I think, in your homework, the car crashing into the wall, that's that type of problem, figuring out the force, or maybe I'll give you the force and you have to find the final or initial velocity. So those are generally just going to involve one body. They will only involve one body. Or you have something like this where you have a collision of bodies and they're moving off in different directions at different velocities. This could be made a little bit more complicated. Let me go back where we did an example like this in class, but let's say that I have two bodies that are moving. Say I have one body that's moving in this direction at 2 meters per second, and then another body that's moving at 5 meters per second. Let's say this is 1 kilogram and this is 2 kilograms, and then they collide, and I'll tell you that the 1 kilogram object zooms off at, let's say, at 8 meters per second. And I want to know what is the velocity of this object. Alright, so this one's very similar to the previous one, except now in the initial state, it doesn't have zero momentum. It now has some non-zero value of momentum. So this is our initial state. And this is our final state. All right, and we'll just say that our initial momentum equals final momentum. All right, the initial is going to be 1 kilogram, that's the mass, times negative 2 meters per second, that's the initial velocity, plus 2 kilograms times negative 5, and this will equal the final velocity, or final momentum, is 1 kilogram times 8, negative 8, plus 2 kilograms times VF. And then you would solve for VF. So my initial momentum here is 2, or negative 2, minus 10, negative 12. So I know this is negative 8. So this has to add an additional negative 4. So it's going to give me a final velocity of 2 meters per second.
Is it negative because it's going that way?
Right, it's negative because it's going that way. Now, you could do it where, this isn't very physical, but like if this zooms off at, say, 15 meters per second, what direction would this object go? Let me show you. You might not know right off, but let me show you. So let's say instead, this one zoomed off in this direction, let's say 16 meters per second. All right, that's going to change my final here. It will be 1 kilogram times 6, negative 16, plus 2 times VF. And then if I solve this for VF, taking this left-hand side, I get negative 12 equals negative 16 plus 2 times VF. And I find that VF is equal to plus 2 meters per second. Whereas before, if I was using these values, have I lost y'all on this? Y'all with me? Negative 12? Oh, that was my initial momentum. So I think I went a little too fast. My initial momentum, which is this state, 1 times negative 2 plus 2 times negative 5. That's negative 2 plus negative 10, which is negative 12. That's my initial state.
Right.
Now, here I never actually finished solving this, but this would be negative 8 plus 2 times VF. So returning back to the original problem, I would have negative 12, that's from this quantity right here, is equal to negative 8 plus 2VF. So VF then would equal negative 2. Right. That means that this object will be going in this direction at 2 meters per second. But if instead of going 8 meters per second, this one was going 16 meters per second, then it works out that the VF is actually plus 2 meters per second. The point being this, that you need to be careful with your signs, because if you put in your signs incorrectly, then the velocity will come out incorrectly. And then also, it doesn't always mean that this object is going to be moving in the same direction. In this case, it actually bounced off of that object. All right? Does that confuse you? I'm afraid it might have. Let me know if it did. Not entirely? Okay. All right. Are there particular questions that y'all want to revisit? I mean, we can do this some more, but before we do, I just want to open up for questions. Momentum is a vector, right? So anytime you're dealing with momentum, you have to include the directions. Now, fortunately for y'all, it's not that way in my other class, but for y'all, the vectors will all be on axis, so you don't have to deal with doing components of vectors, right? Unlike the calculus where you have to do components. So we're sort of done with components for the time being until next semester. All right? You want to do some more energy problems and sort of just have a free-for-all?
Yeah, can we use some from chapter 5?
Mm-hmm. The energy.
Yeah.
You just want to work through examples, or do you want me to go over the topics again? Okay. All right. Remember, there were two major topics. There was work. Work is equal to force times displacement times cosine of theta. Forces can do either positive or negative work. If they're opposite, if the force and the displacement are opposite, they do negative work. If they're in the same direction, they do positive work. And that positive negative doesn't mean direction, because work and energy are both scalar quantities. It means that you're taking away or giving energy to something.
Can you use work and energy like interchangeably?
You can. That comes back to the work-energy theorem. When you do work on an object, you change its energy. So if I throw a ball across the room, I've done work on it by applying a force to it over a certain displacement, and I've given it energy. And it turns out that the amount of work that you do is equal to the amount of energy that you do, or that the object has. So they're not exactly interchangeable, but they're equal to one another. And that's the work-energy theorem. And we use that quite a bit when we're working through problems. Let's look at let's do a conservation of energy problem. You're definitely going to see a couple of these at least. I don't think I've ever had these two chapters on a test all by themselves. So, like, a lot of the chapters have a third chapter, or a lot of the exams have a third chapter in there. That just means that you're going to see more problems. It doesn't mean necessarily that there'll be more difficult problems, but you'll see a greater variety of problems. This should be good for you, I think. But let's see. Now, let's try this one. A man jumps off a cliff 55 meters high. What is his speed when he gets to the bottom? Right, we did this problem in chapter 2. This is a freefall problem, kinematics problem. And before, we had to find the time for him to get to the bottom, and then we had to calculate the velocity, that v equals v naught plus at. But it's a lot easier to work when we're thinking about energy. I have this guy. Up at the top, his velocity is 0, so his kinetic energy is 0, and his potential energy is equal to mgh. And then he jumps off, and at the bottom, his potential energy is 0, because h equals 0, and his kinetic energy equals 1/2 mv squared. Now, what the conservation of energy says is that this energy at the top is his total energy. It's going to be the same all the way throughout. So it's going to equal this energy. So I would just say that the energy initially, which is mgh, or it's Ke plus Pe, but our Ke is equal to 0, will equal to Ke plus Pe, but here our Pe, our potential energy, is equal to 0. And then I can start putting in some values. I have mgh equals 1/2 mv squared. I'm going to erase these things down here at the bottom. Notice my masses cancel, as is usually the case, as is always the case unless you're dealing with springs, and I'll show you a spring problem in a
So
second.
when you do Ke plus P equals Ke plus P, the one on the left is your start.
Right, that's my initial energy,
Okay.
and the one in red is my final energy.
Okay, so you set the.
Initial and final.
Right.
Those equal 0. Oh, okay.
So I was doing it color coded. I was trying to
Will there ever be a time where the connected, like, the word, like, 1 won't be 0, then, like, 0?
Can you repeat that?
Okay. So, like, you know, like, the kinetic energy at the top and, like, the potential energy at the bottom is 0. Like, will there ever be a time where, like, those numbers won't be 0 yet, like, actually calculated?
Right. Yes.
There it is.
Yeah, I'll show you an example in just a second. All right. Right after this one.
Like so, like in the middle of that cliff, would the total answer equal the P at the top?
Right. So if that's the answer to your question, actually, Anna Catherine, is that if instead we're asking a question, what is his velocity here? Here, our kinetic energy would equal 1/2 mv squared, because our velocity is not 0, and our potential energy would equal mgh, because our height isn't 0.
You just add that 7 equal to the.
That's right.
The 1/2 mv squared, like, the potential at the bottom, so it's 0.
Yeah, we'll do that problem next. Let me finish this one up, and then we'll do that one next. Okay? Because that's a variation on the problem that you can certainly see. You probably will see. In fact, so here, make sure that you're up on solving these. I think if you just work through them a couple different times, then you'll be able to do the algebra okay. But let's see. Here we're looking for the speed. If I multiply both sides by 2, I get 2gh equals v squared, and then I take the square root of both sides. So I get v is equal to the root of 2 times g, which is 10, times h, which is 55. So the root of 20 times 55 is the answer not there? Oh, it's 33. Yeah, 33. All right. In this case, in both situations, the initial and the final, one of them went to 0. But let's work through a problem now where, like Anna Catherine was saying, where one of them are, in one case, they're not both 0. Or not one of them is 0. Can I erase this whole thing? And then we'll look at even another one. Yeah. Yeah, whenever you're using the g, whenever you use that variable g, that's always going to be a positive 10. In fact, you know, we're sort of done with negative acceleration. Right. That negative 10 meters per second squared only comes into play when we're looking at like free fall and what have you. Besides, potential energy is a scalar quantity, so it doesn't mean anything to have a negative value. So if we're talking about a problem where I want to know the velocity here, let's say that our height is, I don't know, 40 meters. Then I just say the energy initial, which is Ke plus Pe, is equal to the energy final, Ke plus Pe. All right, this is final. This is the initial energy. Initially, the kinetic energy is equal to 0. All right, so I would say mg times 55 meters, that's my h at the beginning, is equal to 1/2 of m times v squared plus mg times 40 meters. All right, I'm solving this for v. Get rid of my m's, they all cancel out, as they usually do.
Okay, so what's your height?
Yeah, the
So
whole
no one over
place.
40 meters?
Mhm.
Alright.
The whole cliff's still 55, and then I could either say that he drops down 15 meters, or I could say that he drops to 40 meters above the ground. You follow what I'm saying?
Kind of.
I could say, what happens if he falls 15 meters? What's his velocity after he falls 15 meters? And at that point, it would be 40 meters from the ground. But you're always measuring h from the ground. That's your reference point. In fact, you can set your reference point to be whatever you want, but in this class, we've always set it to be the ground, and that's usually the most useful. All right, so I can solve this. G times 55 is 550. Using that positive 10 equals 1/2 v squared plus 400. Subtract 400 from both sides, that's 150. And then multiply both sides by 2. It's 300 plus v squared. And then I square root both sides to get v, which is 17. All right. You feel okay about that? Can I erase? No. Oh wait, just a sec. Everybody get an equation sheet? Yeah. Again, if I'm going too fast, please stop me, okay? Going okay speed for y'all?
Your original formula was like mgh equals 1/2 mv squared plus mgh.
That's right. Right. I just wanted to put in the H's.
Okay.
Make sure I differentiate it. So my initial energy equals my final energy. But then I said, well, this kinetic energy at the top is 0, so I just leave it out because it's 0. Right? And then I have 0 plus mgh equals 1/2 mv squared plus mgh. So you might write it differently each time, but just because some of the energies go to 0, but you're always starting with this. This is your sort of generic equation. Oh, I didn't get that conservation of energy on there. I'll put that on your equation sheet. So you'll have that energy initial equals energy final. That's what it'll say in your equation sheet. That's the conservation of energy. Okay. Now, other problems in energy come up. Oh, here, this is another problem where I have this roller coaster. You want to work through this one as well? Yeah, we have plenty of time. Remember, guys, treat this like a help session, so you can come and go. Like, if you need to go, that's okay. I won't be offended. So here, I have a roller coaster. It doesn't say, but we'll assume that the velocity at the very top is 0. So this is like when you just get started. And I want to know what is the velocity here. So this works out very similarly. I have potential energy here, but no kinetic energy. And I have kinetic energy plus potential energy here. So over here, kinetic energy equals 0. So I'm just going to leave it off completely. All right, so I'll say that the potential energy initial is equal to the kinetic energy final plus the potential energy final. That's going to be mg. I'm going to go and put in the h. 120 meters equals 1/2 mv squared. I want to know what v is. Plus mg times 40 meters. Yeah, go
On this, at each top of the hill is p equals 0, or is it just that?
No, p only equals 0. Which of the points on this graph does p equals 0? G? No. Which one? E, right. So remember, PE is equal to mgh. So anytime that h goes to 0 is when our potential energy is 0, and the 0 point for h is all along here. So it's only at point E does the potential energy equal 0. Where would the kinetic energy go to 0? I mean, I know that it's 0 here at point A, I've already said that, but where else might it be 0? Right at G. So this cart goes down, and it zooms through here, but when it comes back up to the same height where it was previously, all of the energy goes back into potential energy, and there's no kinetic energy. So this first question, actually, where is the speed of the car the greatest? Where is it fastest? A, B, C, or D? Out of those options, A, B, C, or D, where is it going the fastest? Where is the, okay, another question is, where is its kinetic energy the greatest? And that's where it's going to go the fastest. Or where is its potential energy the least? Where is it? D. D, right, of those 4 options. Where, out of all the 7 options, what's the fastest point? E, right, so at E it has no potential energy. That means all of its energy is in kinetic energy. And that's the point where it's going the fastest. All right, we can solve this. Again, just working through these will give you practice and make you fast at solving them, just doing the algebra. I get 1200, 1/2 v squared, it's 400, v is equal to the square root of 1600, it's 40. Isn't that right? 860, yeah, square root of 1600.
Why do you add?
Oh, I didn't add it. Okay, I'm sorry. I subtracted 400 from both sides. And then I multiply by 2. So I get 800 over here. And then I multiply by 2. And then I take the square root of both sides. Yeah. All right? Agree? Right. Because it has no potential energy, so all of its energy has been poured into kinetic energy. Oh, it just wasn't. Out of those A through D, what is its fastest? D is faster because it's the lowest point of A through D. And so since it's the lowest point, it has the least potential energy. Right, the one with the least potential energy. And also, really what you're worried about is it has the most kinetic energy. Right, so that kinetic and potential energy, they always trade off, but they always add up to the same value. And so if one of them decreases by a certain amount, the other will increase by that same amount. Follow me? Okay. Let's clear this out. Let's look at a work energy problem. I don't know if there's one on this one. It doesn't look like there is. Let me make up one for you. Is that okay? All right. Let's say that I have a track that looks something like this. All right. No, that would be too complicated. Let me give you a different one. I think we might have done a problem like this in class. I'm not sure. You'll stop me if we did. Did we do an inclined plane that had a frictional force acting on it? Maybe. Let's do it again. It's a good problem that you could see something like on the test. So, like a slide with a... Uh-huh. But did we calculate the velocity at the bottom? Okay, well, let's just do it anyway for practice. All right, so let's say that I have an object, and then we'll do a spring problem. That's sort of the next big class of problems. Let's say that this is, we'll do a 3 meters, 4 meters here. Yeah, we did do a problem like this. Or was that my 201 class? Did we do this problem? It's okay to do it again? Okay, so let's say that I have this object. It slides down this, this inclined plane, and I just want to know the speed. If there's no friction, then I can say that the potential energy up here is equal to mgh, and the kinetic energy down here is 1/2 mv squared. right? No kinetic at the top, no potential at the bottom. At the top, V equals 0, so kinetic energy equals 0. At the bottom, H equals 0, so potential energy equals 0. So I just say mgh equals 1/2 mv squared. All right, that's going to be m's cancel. 1030 equals 1/2 v squared. So v is equal to square root of 60, which is like 7 point something. All right, that's 8 actually. Fair enough, 8. However, let's say that I have a frictional force, Fk, equal to 1 Newton. All right, I'm going to tell you the mass here. Let's say that this mass is 10 kilograms. And I want to know what is the velocity at the bottom. So now I have my potential energy at the top. That's still the same. And it's going to have kinetic energy at the bottom. But you're going to deduct this work that's done by friction. So you're going to have this negative term, work done by the frictional force. So it's going to look like this. Let's redo it here on the right. mgh, that's its initial potential energy, equals, or excuse me, you're not going to deduct it here. You're going to deduct on the left. mgh minus no, I'm sorry. It depends how you think about this. You have to be careful with your signs. You don't have to be terribly careful, but you need to remember that that work that's done by friction is taken away. It's energy that's taken away from the object. So let's just calculate what is the work done by friction. I'll do it up here. We'll do it slightly differently. The work done by friction is equal to the frictional force, Fk, times the distance over which it acts. So that's equal to 1 Newton. What distance does it act over? 5 meters, right. I know that because this is a 3, 4, 5 triangle. If you forget that, you can just do square root of 3 squared plus 4 squared. That's equal to 5 with Pythagorean theorem. All right, so I lose, due to this frictional force, 5 joules of energy. Now I know that my total energy initially is the potential energy. And that potential energy is mgh, which is 10 times 10 times 3. So that's 300 joules. So it has 300 joules of energy to start with. And so the kinetic energy at the bottom will equal this 300 joules minus the 5 joules. Because when the object slides down the inclined plane, it loses a certain amount of energy. Initially at the top it had 300 joules, but then it slides down that inclined plane, and the frictional force does work on the object to take away energy from that block. And it takes away 5 joules of energy. And so whereas before it had 300 joules at the top, right. No. Yeah, that's what I was going to do initially. But really, you just want to be careful about the signs, because if you did 1/2 mv squared minus the work due to the frictional force, that work due to the frictional force is actually a negative value. So then you have like a minus of negative value. So that's why I backed up a little bit. The work due to friction is negative, right? So if you say minus the work, then it's minus a negative value, which would be positive. But just, right, minus 5, yeah. The work done is 5 joules. It's actually negative 5 joules. But, yeah. Yes, I think we're okay. No?
Well, I thought it was right, right?
I think you're right, yes. It's sort of splitting hairs. I just want to be careful. Okay? So here my kinetic energy is 295 joules. And then if I want to know the velocity, I say, well, this is equal to 1/2 mv squared. All right, and solve that for v square root of 295 over 5, whatever that is. That's the velocity at the bottom. No, the other one was the velocity at the bottom if there is no frictional force. Probably going to see a problem like this. Oh.
Alright, I'm so confused. Why are you subtracting from the potential energy? Why would you be subtracting from the kinetic energy? I don't get that.
Okay, the amount of kinetic energy, you could subtract it from the kinetic energy if you wanted.
No, but then,
No, you can't.
but then again,
You don't know.
5 is like 295.
Well, that is not your answer.
Well, you have 300 joules at the top. Like, that's what we know, right? 300 joules. And then as that block moves down, it gradually loses 5 joules of energy. So as it slides down the inclined plane, by the time it gets to the bottom, we know that it has 5 fewer joules of energy at the bottom. What did you get when you did it your way, Anna Catherine?
Well, I stopped, so those are wrong, but
It's good to get things wrong sometimes. Helps you learn.
So that 295 is the amount of work done.
at the bottom.
No, not the amount of work done. The work done is 5 joules.
Okay.
By the frictional force. That's the 295 is the energy at the bottom.
So at the top, the kinetic energy is 0.
That's correct. Yeah. All right.
What I said, V is equal to square root of 61, which is 7.8.
That's not right. Square root of 61. Well, I don't think that's right. No, that's not right. See, you are adding your 5 joules.
Yeah.
And you subtract it from the 300. Try not to get bogged down in the signs too much. Just remember that as it goes down that inclined plane, it's losing energy. And so you have to subtract that energy from the total energy.
So it's equal to NGH minus WF is equal to 100 squared.
Yes. You're very likely to see a problem, something similar to this, where you have a non-conservative force, that is a force that does not conserve energy, that you lose energy, that acts on an object, and then you have to find out what is its new velocity. Alright. Y'all okay with that? Alright, let's do a spring problem. Okay. No, wait. Y'all seem tired. Y'all tired? Yeah.
That's 7.8.
That might be right. That sounds right.
Okay, because when I did it this way, I did the square root of 295 divided by 5, and I got 7.68.
Yeah, that's right.
I'm like, that you would just say, where is the velocity?
What is the velocity of the
Yeah,
block?
I'm just,
Alright, can we do the spring problems? Y'all okay with this? There's a problem in your homework, I believe. You double check that. That's similar to this. Chapter what, 5? Lots of conservation of energy problems. Oh no, there's not one in your homework like this, actually. Alright, but we did do one in class. Okay. Let's do some spring problems. Or we'll do one spring problem. We're almost out of time. I have to leave right at 2. I'm sorry, I have a meeting at 2. But, is that okay? Do a quick spring problem?
yeah.
Alright, so let's say I have a spring. It has a spring constant equal to 100 newtons per meter. Remember, that describes how stretchy the spring is. So, like, a big K value means it's very difficult to compress your spring. A small K value means it's very easy to compress a spring. So, a slinky, small K, springs on your car, big K. All right, that's our spring constant. Let's say that I stretch my spring by a certain amount, and we'll say that I stretch it by 50 centimeters, or 0.5 meters. I have a mass on it that is 1 kilogram, and I want to know just how fast does it go. So it would look something like this. I have this spring, I have this mass of 1 kilogram. This is its equilibrium position, and I stretch it back to x equal 0.5 meters. It's actually negative 0.5 meters in this diagram, but it doesn't matter because you square that, so that negative goes away. And I just want to know, when it comes here, what is the velocity? All right, I could also ask, what is the velocity, say when it gets here, say at x equals 0.1 meter, what is the velocity there as well? So I'll call this v1, and I'll call this v2. What is v1 and what is v2? In both of these cases, I say at this point, I have only potential energy. That's elastic potential energy, not gravitational potential energy. At this point, I only have kinetic energy, right? Because the spring now is at its equilibrium position. And then at this point, I have both kinetic energy and potential energy. And all three of those energies have to be equal by this law of conservation of energy. Okay? Because I have my spring is stretched a certain amount. Anytime that I have x not equal to 0, right? And over here, the kinetic energy is 0, just because that's what I told you, that it's not moving. I've compressed it fully, and I'm about to let it go, and so it's not moving right there. All right? So first, to find V1, I say the potential energy of the spring is equal to the kinetic energy. That's setting this energy equal to this energy. 1/2 kx squared, 1/2 mv squared. By the way here, guys, don't forget that x is proportional to v. So if I increase x by a certain amount, I increase v by the same amount. We talked about that in class, just briefly. It was in the concept test. All right, I can solve this for v. Cancel out my halves on both sides. I get 100 times 0.5 squared equals m, which is 1 times v squared. That's 100 times a half squared, which is 1/4. That's 25 equals v squared. (5 meters per second). So at this point, v is equal to 5 meters per second. All right, now to find V2, y'all with me so far? These are very similar to my gravitational potential energy problems, except now instead of having mgh, I now have 1/2 kx squared. They're different though because your masses don't cancel, so they're a little bit more complicated to solve. Bree, you look like you have a question. You have a question? The 0.5? Okay. Right here, I have only potential energy. The block isn't moving here. I have only potential energy, and that's what I wrote here, the potential energy of the spring. And that potential energy is equal to 1/2 kx squared. And that'll be on your equation sheet on there now. So my potential energy is 1/2 of k times this distance squared. That's just what it is. Does that answer your question? You sure? Now to find V2, this is one of those where you have to account for kinetic and potential. So I say potential energy of the spring, that's this potential energy, is equal to kinetic energy plus potential energy. That's looking at this third scenario. So that's 1/2 kx squared. I'm going to call this x1 is equal to 1/2 mv squared plus 1/2 kx2 squared, where this is going to be x2. And I can simplify it a little bit. I get rid of my halves here, here, and here. I'm looking for v, so I'm going to do kx1 squared minus kx2 squared equals mv squared. That's 100 times 0.5 squared minus 0.1 squared. That's not the same as 0.4 squared, by the way, so be careful with that. That's equal to m, which is 1 times v squared. And we just want to practice these to make sure that you can do these calculations. So 100 that's 24. Root of 24 is v. .9. All right. Right. Yeah, so we're comparing one scenario to another situation. So we're comparing the energy over here, where the velocity is 0 and the position is 0.5, to the energy over here, where the velocity is not 0, it's actually what we found to be 4.9, and the position is 0.1. No, that's just this good. Okay. All right, guys. Sorry, I have to call it quits, but I guess we won't have a. Well, no, we'll have another help session next week. Is that right? No, when's our exam? Oh, it's fall break. Yeah, I won't be here next week. Sorry, but remember, I am here to help y'all. Okay, so like in my office, if you need help, I'm here to help you. So if you're still having trouble, then please come see me. You will see these on the test.